And okay, the first speaker in this morning is Thiago Macieira from Intel. And he's going to talk about writing better code with help from Qt and the compiler. So please, Thiago.
Hello, everybody. Hope everybody can hear me. This is impressive. Nice to see so many of you here. I see several familiar faces. And I see that the room is still getting full, so while people get in, if everybody wouldn't mind, if you have a seat next to you, move over to your left, to my right, so that we can make room for everybody who's coming in. Another thing I should note, this is the same talk as I gave last year. So if you saw it last year and you still remember the techniques, you don't have to see them again. They're the same techniques you can still use today. They're still valid. If you want to refresh your course, you're welcome to stay, of course. If you want to learn something new, I'll be talking. There's at least one new slide in this presentation, something that was invented, contributed by a colleague of mine at Intel in the last couple of months. So it's always great to be at, well, this is the first Qt World Summit, but the Qt Developer Days, at least, I've been presenting them for a couple of years now, and it's so great to see so many familiar faces. It's one of the best events I've ever attended, because everywhere I walk, there's always somebody who is asking interesting questions, and the work we do in the Qt project, and I did previously at Trolltech and Nokia, is so rewarding to see you guys using it. So without further ado, let me properly introduce myself. I'm this guy. As you can see from the picture, I've been around high tech since I was fairly small. This is 1982, as you can see. That, for those of you who are too young, is not a computer with a printer attached. That's a typewriter. The keyboard was pretty deficient. It did not have 1 and 0, right? That you could get away with just the letter L and letter O. So I've been around open source for at least 16 years, probably more. I started doing some work. My trajectory in this is that I wanted to find something new to do, and I decided, let's try IPv6. And by the way, for those of you who are following the IPv6 trend, we're out of IP addresses as of 2 weeks ago in North America. Europe was a couple of years ago, Asia 4 years ago. If you want to get a new block of IP addresses, you need to go to Africa. So I wanted to find something to do. I started looking into IPv6. I decided, let's make a browser work on IPv6. Mozilla at the time already had support for it. So I decided to look into KDE. KDE's browser, Conqueror, did not have support for IPv6. So you see how that got me to working with Qt. One of my first contributions into Qt itself, before I even started working for Trolltech, was exactly that type of functionality, trying to make the class we now know as QTCP socket, and back in Qt days was called, Qt2 days was called just QSocket, speak IPv6 natively. Fast forward, I got hired by Trolltech, went to live in Norway for 6.5 years, and then when other things happened, I moved to Intel, and I'm now living in the United States. So I flew over from the United States to present yesterday at LinuxCon. I flew in the evening, arrived here, and now I'm here to talk to you guys. So why am I giving this presentation to you? I want to talk about how you can improve code generation. Most of what I'm going to talk about is about Intel platforms. So small note, it works on other platforms. There are techniques for other platforms, you just will not be hearing them from me. You can look up the documentation, it's fairly more or less the same. Another thing to note, this is not an assembly lesson. I will show a little bit of assembly just so you can get a feel of what you're generating, what I'm talking about, but this is not an assembly lesson. So this is an example scenario. This friend of mine went to an interview, and raise of hands, how many people went to interviews and they had programming questions? So mine was, by the way, with Matthias Ettrich. I think most of you remember him. He gave me the task of reversing a string. But this friend of mine had a more complex question. He was asked, you have 2 megabytes of data, just so that it's not trivial, and you want to calculate how many bits are set in this whole chunk of data. How would you do it? And I mean, they just said memory usage is not a constraint, so that you can use tables, whatever. So who wants to suggest a solution? I know this is intimidating. Come on, guys. Counting bits.
Just make a table of the first 256 bytes and how many bits are set in each.
There you go. That's a very good. So that's a very good technique. So I probably gave it away by saying key and create tables. So the solution, one of the most efficient ones, is create a table of the first 256 bytes. So 256 possibilities. So 1 byte, how many bits are set in every of the 256 combinations of 1 byte? And then you just iterate, adding up. It's a very elegant solution, by the way. One that the examiner would be very pleased to hear you talk about. There's something in the back that somebody wants to suggest?
Well, there's something from Heckman. I don't know exactly how it works.
Sorry, something from? I couldn't hear you. Something from where?
There's some solution from Heckman where you do something like shifting.
Yeah, something about shifting. So if you actually go on Wikipedia, there's a lot of solutions for this problem. One of them, the simplest one, the most, let's say dumbest, but the simplest one is to just, AND with every one of the bits and add them up every time you see them. The operator double bang here, just, convert a value from non-zero to 1. Or the solution of the table, which would also be, sorry, this is not a solution of the table. This is a solution of the, there's some bit magic here. The interesting thing to note is that this one takes 8 AND operations and 8 additions. This one will run for as many bits as you have set. So there's a difference in complexity. If your data is very sparse, only has, very few non-zero bytes, this is actually faster than that one. The table solution would run equally as fast with any data, and would actually probably be faster than any of these solutions. So the table solution is a very good one. Now, I remember this friend of mine, so yeah, by the way, I'm sorry. The lookup table, that's actually the better solution. So you create a count table. In this case, I went further and said, instead of reading 1 byte, I'll read 2 and be twice as fast. You'd be impressed just how much this makes a difference. By the way, last week I was working on something I wanted to improve performance of. I started with the existing Qt code. I got a number, I think it was something like 5 million clock cycles per iteration using the Qt benchmark. Then I wrote my specialized code. I got it better to around something like 3 million. And then I did this table doubling, like this, and it was 3 times faster, just by doing the doubling. But anyway, my point was that when this friend of mine talked to me about it, my answer was something that the interviewer in his question would have gone like, what? My answer was, use the instruction that does it. Like if you answer this in the interview, the guy's going to like, you're cheating. Yeah, this is good. I mean, this is the fastest possible solution for your problem. And by the way, this instruction runs with even 64-bit input, so you go 8 bytes at a time. But it defeats the purpose of the interview, which I don't care. Right? I'm not in the interview. I actually want the fastest code possible. So if you look at QBitArray, for example, today, it has, I believe, it has some pop count instructions there to do exactly this kind of thing. It doesn't cost as much to do it, to just write the code, and then you've got faster solution. The note here is when this instruction turned up. This is going to become important for us because many of these newfangled things that the processor comes and tells us about, they are in processor versions that may not be the one that your compiler is targeting. So you have to know when and how to use it. So that's exactly it. So how do you use it, the instruction? Well, the simplest solution is, of course, write assembly. I'm not going to tell you not to. If you know how to write assembly, do it. If you know how to insert assembly in the middle of your C++ code program, do it. I'm not going to tell you not to if you're comfortable with it. It will allow you several advantages, like you control precisely the timing of the instructions. You control precisely what's going to happen. You're not beholden by how the compiler behaves or not. On the other hand, there are a couple of problems with assembly. The assembly, if you're writing code like we are in Qt, trying to make it cross-platform, you run into different versions of the assembly itself, especially when we're talking about Visual Studio and GCC-like compilers. The assembly block inside your C++ source code is different. And moreover, on 64-bit, Visual Studio does not allow you to write assembly. You have to write a separate file, which has a separate syntax from what you would see with GCC. So using the intrinsics actually allows us to embed assembly inside your source code. And they just look like regular functions, as you can see. So if you don't want to control precisely the timing, you want to leave this to the compiler will do it. With the added advantage, on the other hand, that if the compiler knows better than you do of the timings, of the loads, and what happened before and what happens after, it might actually generate better code than you would. And if the compiler is improved for the next generation of processors on how, because they changed over time how things are affecting each other, your code without modification will adapt. So these are some of the advantages of using intrinsics. So intrinsic is a function that isn't defined anywhere. It's a function whose body is replaced by the compiler. So these underscore built-in are defined by GCC itself. You have to look up GCC source code to find them. The underscore MM, and I believe MM comes from multimedia because these things started showing up with MMX back in the 90s, which for those who never looked at it means multimedia extensions. They are defined in the Intel manual. So if you go and download the Intel processor manuals, you're going to find the description of them. I'm actually getting ahead of myself because I should be talking about that later. The other question is not just how to use it, but when. I mentioned that it exists in different compiler versions. So you can just say, I don't care, I'll just use it right now because I know what computers I'm targeting. I know what processors I'm targeting. I'll just use it unconditionally. Or, if you don't know how to do that, if you want to target the broadest range of processors possible, you would have to check CPU ID. You can do that. The only issue I want to tell you about is that the CPU ID is actually pretty slow. You're not supposed to call it in a loop. You're not supposed to call it in critical sections. You're actually supposed to cache its result. You can ask the linker for help. I'll show about that later. And you can check if the surrounding code already does it. And by that I mean, if the compiler is already generating, for example, SSE2, might as well do it. Why would the compiler already be doing SSE2? Well, first of all, in 64-bit, it does. And second is that your user might have actually turned it up. So, show of hands, how many Gen 2 users here? Okay, not that many. But, Gen 2 users just tune everything to the CPU they're running on. Might as well you do it as well. But if you're trying to do generic, you can't do this. So how do you choose which solution you're going to use? You have to check which CPUs your code is supposed to run on. So if you're working on a generic piece of code that is going to run on almost everywhere, that choice is everywhere. You have to understand what the issues are with the features that each CPU will support. You have to understand which compilers and tool chains your code will be compiled against. And that's exactly the issue I talked about before. If you were writing assembly, you could write anything, but you would have to write different flavors of assembly to compile with Visual Studio or not. And of course, you can't expect compilers written 5 years ago to know about the CPU extensions that were published last June. So you have to check which of these functionalities the compiler already supports. Fortunately for us here, Qt already does all of this checking. So the interesting thing is that you can check which libraries you're using if they have this ability to support it or not. GCC does by itself. Qt does. Unfortunately, a private header. So I'll actually show about it, but if you want to use a private header, go ahead. If there's a lot of interest, we can consider making it public. I said this last year. It hasn't been made public yet, but I don't think that many people came to talk to me about it. Another thing you need to check, again, like I said, if the CPU ID is more expensive than the benefit you get from improving your code. So yes, do not do this blindly. Benchmark. You have to figure out, you have to benchmark and see which solution actually produces the better result. So going back to the experiment I was doing last week, after I had finished with the table, I decided, let's try some instructions from the Intel manual. My first solutions were all slower. Right? So I had to continue to hack around it and figure out which solution would actually produce the best code. It's not just that I'm using instructions that it's suddenly faster. There are other things that you have to take into consideration. So like I said, they exist on other architectures. ARM with Neon also has a very big library of instructions, of intrinsics that map to the Neon instructions. Same thing with PowerPC and the AltiVec. Vec probably means for vector instructions. They do have that functionality. Like I said, you will not be hearing them from about really the details of them from me. You can look at them up yourself, yourselves. Just be careful, especially, you know, as time goes by, not so much, but when I was at Nokia and we were trying to do some Neon coding, the compiler was really bad. So GCC produced ugly, really ugly code that actually was slower than the code without. But if we wrote assembly manually, it was actually faster. So you have to check your compiler to see if it's producing good code too. So how are we going to learn about these intrinsics? I said before, you can just go and download the manual, and when you're out and about somewhere in the middle of, I don't know where that is, you can read the manual. Right? So you can be like we all are, antisocials, not talk to your friends, and just go and read the manual. This, which the guy is reading here, is the Intel 64 and IA32 architecture software developer manual. So if you talk to somebody like me working for Intel and they talk about the SDM, SDM has nothing to do with pain. Well, maybe. This is the software developer's manual. The other one we talk about is the SOM, the software's optimization manual, which has mostly instructions for compiler writers, but it's something that you might want to take a look at least once in your lifetime. These are published a couple of times a year as when there are updates. The latest one happened in June of this year, shortly before the launch of the Skylake architecture, because like Skylake had new instructions, they wanted to publish and say this is exactly what's going to exist in that compiler. We published also the instruction set extension manual. So it's a separate manual saying this will show up in some future version of a processor. So compilers and people can start optimizing and figuring out what they can do with this. So if you go and open this document, and you look up the pop count instruction, you're going to see something like this. Actually, there's a cut here. There's a lot of in between explaining the opcodes, what the instruction does. It has a Pascal-like explanation of what the instruction does and how it operates, where it loads, etc. What's interesting for us is that you're looking for the instruction name, right? You see which versions exist, 16, 32, and 64-bit. And you look at the bottom of that section, you're going to find the intrinsic equivalence. It just looks like a function declaration. And that's the beauty of it, because it's like you're calling a function. Right? So it's telling you that given a 32-bit argument, right, unsigned int, it will return an int, which is the count. And if given a 64-bit input, it will also give you an int. In this case, of course, too many bits to return a number from 0 to 63. Sorry, 0 to 64. But this is how you learn it. So we are going to take that and try to use it in our code. So a couple more examples of what you can do. The example of the pop count, like answering the interviewer's question, how would the code look like? So I have some data, right? I said 2 megabytes of data. And you loop around it, right? And you call pop count on that data. Just a small side note, this cast here could return unaligned data. On x86, that's fine. We can load unaligned data. It's faster if you align it. So I just didn't want to make this complex here. Don't do this in other architectures, because you might crash. Another example is calculating CRC32s. Calculating a CRC32 polynomial is not a trivial task. There's a way to do it. There's a lot of functionality. But what you would do is you start with a 0, right? You take some data and the current hash, and you update it. So you're just looping around the same data, and you return a hash. Where do you think I would have used this in Qt? QHash. Yes, QHash. So if you're running a Qt 5.4, 5.5, automatically it will start using the CRC32 instruction to calculate hashes. Now, it doesn't calculate CRC32 if you don't have the instruction, because that would be slower than the old code. I actually do not care about the properties of a checksum. What I do want is a hash, just something that more or less spreads around the data. This is very, very fast. So when you Q-hashing any input, it's just running this instruction and loop behind the scenes. Which unfortunately for some people means that your unit tests will produce different QHash results run on different machines. Let me explain. If you run a unit test that depends on the order of iteration on a QHash, which is the problem? You should not do that because the order is supposed to be random. If you write a unit test that depends on the order, it will produce different results depending on which machine you're running. So do not depend on the order of iteration on QHash, because it might change depending on where you're running. So the beauty of this, like I said before, I'm going to reiterate, it's just like a function. I don't care that this expands to one. Actually, I do care. But it doesn't show up here that this expands to assembly. It's just doing what it's supposed to do. It's available for almost all of the x86 instructions. There are a few of the older ones back from 8086 with 16-bit days that are not available, but most of them are, including some that were available then, like rotation of bits. And doing like this, for example, we just wrote it once, but if the compiler is actually unrolling this loop, and it might, as an optimization, it will duplicate your instruction. It cannot do that with assembly. It can do this, can do it like here. And one of the advantages of not writing assembly is not making assembly mistakes. So you can't, jump to undefined labels, jump out of the function, fall off the edge of the function, forget to pop some registers and things like this. The compiler will take care of that for you. So this is how you use it. The question is now, where can you use it? For all compilers, you have to, like I said before, check whether they support the instruction. For example, AVX2 has existed since GCC 4.7, and AVX512 Foundation since 4.9. So this is one of the things new since last presentation. Clang 3.8 now supports this functionality. Because you don't, since in these two compilers, Visual Studio and the Intel compiler, you can just use them anywhere. The compiler will generate the right instructions. For GCC and Clang, you need to decorate the function saying where this function will be run. This has an interesting property that the compiler can also tell if you're calling from where you shouldn't be. If you have an older version of the compilers, you actually have to pass extra compiler options to allow it. Those extra compiler options will produce a lot of this code elsewhere. So you have to be careful when calling into this file at all. So how did I do this for Qt? Right, I've been talking generic. I've been talking how you would do it in general terms and plain data blocks, etc. How did I use this in Qt? So here's how. I talked about QHash. So here's the exact simplified code version from QHash. There's a macro that you can use with if, with hash if, right? Which tells whether the compiler has the functionality and will allow you to generate code in that position, given the previous table. Is this compiler this version, or is it the compiler option passed, etc. Then there's another macro, the Qt function target, that expands to the attribute decoration if necessary, or empty if it's not necessary. So if you're using the Intel compiler or Visual Studio, it expands to empty. And then I have this function called crc32 that just does the implementation. The implementation you can look up on qhash.cpp. It calls the 64-bit version for as long as it can, and when less than 8 bytes remain, it runs the other 3 until nothing remains. Hash else, if this instruction can't be done, Q unreachable. Why Q unreachable? Like I said, if you don't have the instruction, we run the old algorithm, which is faster than calculating crc32. Now I'm going to show you some of the techniques that you can do at runtime. So I told you how to write the code, but you need to understand how and when to use it. When is the processor allowing you to do this? So we call runtime dispatching. It's actually simple. Detect which CPU you are in, figure out which implementation is best, and run it. The devil is in the details. So how do you do it? Magic goes here. So if the CPU supports SSE2, call the version that runs SSE2, otherwise call the plain version, right? This is how you would do, for example, using another intrinsic from GCC itself. GCC will tell you whether the CPU you're running on supports SSE2, right? This doesn't work with other compilers, though. So you need to have a solution that works with all the compilers. And this was our problem in Qt, because we needed a solution that works with all the compilers. So we wrote one. It's in, I'll show you the header. I can tell you the header at another time. But we have this function that called QDetectCPU features. It's in Qt core. And it fills in a variable that used to be an int up until a month ago. It's not anymore. And so it checks if the feature is 0, call it, otherwise return it. So this means actually it's a very fast implementation. It loads a variable and does an unlikely jump or return it. So the CPU ID goes in there. It's all hidden behind the scenes. All you need to do is call this function, and it will return the bits of whether the functions are set. But I'm not satisfied. I'll show you something later. You can check surrounding code. When you download this presentation, you're going to see the command line there that is there. But basically, what I wanted to tell you is that the compiler has a bunch of defines that will tell you what it enabled. So if the compiler is telling you, for example, SSE 4.2 is enabled, well, I might as well use it. So if you combine these two functionalities, the macro from the compiler and the runtime dispatching, you get the solution we have inside Qt right now. This is a macro, right? This is a macro. If you're familiar with the creator syntax and you can remember, blue means macro, right? So it's calling a macro with something, right? Which checks both. It checks if the underscore underscore SSE2 underscore underscore is defined. If it is defined, it's unconditionally true, and I can call this. And by dead code elimination, the compiler never calls this other function. And if this is this other function is also static, by dead code elimination, the function is gone. So your code doing like something like this, and you compile it for 64-bit, does not even carry the older version. Now, if you're running on 32-bit, for example, it will not do this at compile time. It will call the other function and verify when to run it. I said that you can ask the linker for help. And this is a nice, interesting feature that works with modern versions of GCC and ICC. I actually need to retest it with Clang. But you tell the compiler that when you call, for example, memcopy, I want you to call this other function first and figure out which one is the best implementation. It will return a pointer. As you can see, it actually returns a pointer, right? And returns a pointer to the function. This happens once in your application, because then it saves in a global place. Anywhere in your application where you're calling it, it will just jump into the right function. So like I said, magic goes there. It's called ifunc, which is short for indirect function, because it calls via function pointer. This is kind of ugly. I just wanted to show you a bit of a C++14 solution. When I first presented this, I was in an Intel internal conference, and Linus Torvalds was present, and you know he doesn't like, and this is an understatement, C++. So I just wanted to show how this would look like in C++14. Yeah. So, you know, using decl type to declare more functions and the automatic return type deduction. Not being satisfied with this, the GCC guys went further and made another functionality that uses the attribute target, like I said, and you define two functions with the same name, differing only in the attribute. And when you call it, the compiler automatically generates what I showed in the previous slide. It generates the dispatching and detection function for you. You don't have to do anything. So all you have to do is call bit count. It will define by itself to figure out which compiler am I running, which versions can I run, which is the static, which is the what is runtime, and we'll call it. Done. And another feature that exists and actually is a bit hidden, what you can do, and this is something we're requiring Linux distributions to do for us, is compile the library, the entire library, multiple times. So you can ask the linker, at least on Linux, to have multiple versions of your library. This actually is a hard-coded list. So this list which you're seeing here, I did not write this. This is hard-coded from the compiler, the linker itself. So it's a nice hidden feature that has been there for a couple of years, or a decade. So you can see when it's searching for a library, it will hit here, for example, this is the one that interests me, ssc2/ the same library name. So you can have a more specialized version of your library compiled with more functionality, generating faster code that will run on a subset of all the architectures. And if the linker finds it, it will load that instead of what it actually did load. So like I said, we're actually requiring this of Linux distributions because on 32-bit Intel platforms, we want them to do exactly this. The SSC2 version of QtCore and QtGUI are much, much faster than the regular versions. So we actually force them to do this, and we provide a way to having the fallback. And a colleague of mine did the same thing for EVX2. So this feature is coming in a new version of the linker, and it's going to work both on 32 and 64-bit. So you're going to be able to have a 64-bit library on an EVX2 subdirectory. So, to finalize, this is how you cheat in interview questions, right? So if somebody asks a function, a question like this, you know how to answer now. Right? So how would you write a function that returns a 32-bit random number? You call rand, no, that's actually a pretty bad implementation. How would you zero extend a block of data from 8 to 16-bit? Or how would you calculate the next power of 2 for a non-zero integer? How do I answer these questions? Somebody wants to venture a solution? And hint, this is a tricky question. You know why you're here in this session. What's the answer for all of them? Use the instruction. Thank you. So I chose one in particular here. How do you calculate the next power of 2? And you could do this. Trust me, it works. You're going to scratch your head like, oh, that can't be. That can't be. Does this calculate the next power of 2? It does. Where did I find this code? Inside QByte array. That's how it calculates how to grow a block. So when you're appending data to a QByte array, or a QVector, or a QString, it's the same code. It grows towards the next power of 2. And as you can see, 5 shifts, 5 ORs, plus a decrement and increment. How can I improve this? I use a function that finds the highest bit set, and I return, of course, the one after that. That's why it has a 2 there. So summary, learn from the manual. If you actually want to write highly specialized but highly performant code, take a look at the software manual. Take a look at what you can do, what the processor can do for you. Intel invests a couple billion a year to making these things work. So might as well take a look at it and see why you're paying for it when you buy a new laptop. It's not the megahertz that count, it's the new features. Oh, it's actually the wattage as well. So you can check the CPU at compile time, at runtime, so both times, and dispatch to the best implementation. Or you can use a library like Qt and compiler linker tools. So with that, I'm going to stop, and I'm going to see if you have any questions. Any questions here? So if Intel will never be satisfied. So the question is, the maintainer, let me just paraphrase, will the maintainer be satisfied if your solution is not generic? I'm not asking you to write Intel specific code. I'm asking you to optimize. So you add the extra version, right? So you're going to do that runtime dispatching. What I had before, can you switch back to my slides, please? So what you had in this here, where was it? Here. No, not this one. Here. So you do check at runtime which version you have. So you're satisfying both. You have the generic version which will work everywhere, and you have the version that's specialized, if possible, for that architecture, which runs better.
So if you have these features built right into the code where it chooses a code class, how do you test those versions?
How do you test both versions to verify that they work, more or less? Well, you wrote your unit tests. And also, this particular version here has no instrumentation. But what you could do is, in your unit test, you actually call them directly, and you verify that the result is the same. This is what I do. So when I'm trying to optimize, I open a new benchmark, a new CPP using QBenchLib, and I write these functions one by one. And in benchmarking them, I also verify that the result is this expected one. Once I find out which version is the best, then I actually can copy it into the Qt source code and use it. But I did verify which result is, that the results are correct when I wrote it. Any other questions? I just wanted to... Yes?
I noticed you use Q-unlikely in there.
I use Q-unlikely in there, yes.
At what point do you start to see a benefit from that?
Well, at what point do you see a benefit from Q-unlikely? I don't know. The Q-unlikely macro tells the compiler that it's unlikely to be true. So if you look at the assembly, sometimes it actually produces better code when it knows it doesn't have to do something. So it actually pessimizes the other code path. In real terms, I don't know how much this makes a difference.
Actually ends up removing the jump instruction.
Sorry?
It actually ends up optimizing the code so that it removes the jump instruction. It reverses the code and it removes the jump instruction.
Yeah, so he said that it optimizes the code so that it removes the jump instruction, or some of the jump instructions. Yeah, if you look at the assembly, it does make a difference. In practical terms, whether that assembly runs faster than otherwise, you really have to benchmark to see.
So you mentioned probably
Unaligned data, yes. How do you align the data? That's a subject for another presentation. You have to take, like, let me just find an example. No, not this one. Where was I? Here. So you probably take the pointer, right? You copy it into an integer, like QUint pointer, and verify the last bits. You know how many iterations you have to do before, and you use the bigger version of the instruction. We can talk about this, and I can show you code that does it. We have some examples inside Qt that try to align. However, let me give you a warning on this one, and thank you for your question. Sometimes the overhead of doing the alignment, the prologue and the epilogue of the functions, is higher than the cost of reading unaligned. So again, benchmark. Because sometimes your optimizations are good, but the overhead of getting into them completely offsets the benefit you get from them. One last question, if anybody has them. Does anybody want to see assembly? Okay, so you said yes. One of the questions I had here was, how do you zero extend a block of data from 8 to 16-bit? Where would you see that in Qt? It's QString from Latin 1, also known as QLatin1 string whenever you use it. So this is a very common operation, and I decided to optimize it. So how do you zero extend normally? This is what existed in Qt a couple of years ago. Well, just, do it. And the interesting thing is that the compiler actually optimizes this. It's highly parallelizable. There's no interdependency between elements. So the compiler just does it for you. The compiler is smart enough to use the assembly instructions. So this is what it did. Right? So it actually did called the unpacking. Right? So you see the P parallel or packed unpack low and high bytes to word. So it actually did the optimization. The difference is, as you can see, different compilers did it very differently. And you can see that Clang here, and this is an old slide, as you can see, it's 3.4, did stuff that doesn't make sense. Trust me, right? You can take a look later and look for yourself. But trust me, what the hell is it doing? So what you do is, you let the compiler do it, learn from the best, and then you do it yourself, right? So what I did is exactly that. I looked into the source code, what the assembly the compiler generated. This is interesting. Load, unpack, save. Unpack, save. This is exactly what QString does now today. So if you look at qstring.cpp, you're actually going to find exactly this code there. So we just rewrite it using intrinsics, and now the result is more consistent. Better or worse? Benchmark. So with that, thanks for coming. I'll be here until the end of the day. I'm sorry I wasn't here yesterday. You can contact me via email or social media. You can stop me anytime in the hallways and ask me further questions. And I'm always on the mailing list if you want to ask me more questions. So thank you, everybody, for coming.